Hello everyone. If you're new to this channel, welcome. If you are an existing subscriber, welcome back to this wonderful channel called Physics Man, your one-stop solution for everything physicsy. Whether you're new or old, I need to make a request over here. Please motivate me enough to make better content every single time. How can you do that? Well, for a starter, you can give me a thumbs up. It wouldn't cost much, man. Or you can share this video with your friends and family. It wouldn't take much effort. Or at least you can think of something nice to write in the comment section. That wouldn't hurt much. Or at least subscribe to this channel and press the bell icon, man. That's the least you can do. I hope you have done all of them. And without any further ado, let's continue with our read along of chapter number 1, electric charges and fields. Okay, so we have learned that there are positive charges and negative charges. Like charges repel and unlike charges attract. So we have talked about the nature of the forces between the point charges. But we haven't talked about the quantitative statement about the forces acting between the point charges. That's what we're going to do in this video. Coulomb's law is a quantitative statement about the force between two point charges. When the linear size of the charged bodies are much smaller than the distance separating them, the size may be ignored and the charged bodies are treated as point charges. We have discussed this already in the previous video. This is the second time they are mentioning the same thing over and over again. Coulomb measured the force between the 2 point charges and found that it varied inversely as the square of the distance between the charges and was directly proportional to the product of the magnitude of the two charges and acted along the line joining the two charges. So Coulomb, when he did experiments, he found that if these two are point charges, okay, we are calling it point charges because the diameter of the sphere is, or the radius of the sphere or the diameter of the sphere is very much less compared to this distance, which is r. Okay, so these are the 2 point charges q1 and q2 in magnitude, and the distance between them is r. Then he found that the force between them is proportional to the product of the two charges. Also, it is inversely proportional to the square of the distance between them. That is, force is proportional to q1, q2. These two lines represent that we are talking about the magnitude and not the polarity. And it is inversely proportional to r square. If we combine these two, we get force is proportional to q1, q2 divided by r square. Now, if I remove the proportionality sign and I bring equal to sign, then I have to bring in a constant of proportionality. So this will come out to be F is equal to K Q1 Q2 divided by R square, where K is the constant of proportionality, or it's also called electrostatic force constant. Let's continue. Thus, if 2 point charges Q1 and Q2 are separated by a distance R in the vacuum, the magnitude of the force between them is given by this. This is the magnitude, but they also told about the direction. The direction is always along the line joining the two charges. That means the force will be along this line. It cannot be like this. It cannot be this way. It cannot be this way. It will be along this. So if they are like charges, they will repel. That means the force will be this way and this way. Yes or no? But if they are unlike charges, then they will be attracting each other in this manner. Anyway, how did Coulomb arrive at this law from his experiments? Coulomb used a torsion balance for measuring the force between the two charged metallic spheres. What is a torsion balance? A torsion balance is a sensitive device to measure force. It was also used later by Cavendish to measure the very feeble gravitational force between two objects to verify Newton's law of gravitation. Yes, the same device, torsion balance, was used to find Coulomb's law, also to verify Newton's law of gravitation. But the funny thing here is that the equations are similar in both the cases. Here we see that F is equal to K Q1 Q2 by R square is the equation from Coulomb's law. Similarly, the Newton's law of gravitation gives us the equation for force, gravitational force between two bodies, which is given by F is equal to capital G m1 m2 divided by R square. It's very much similar. So the same device is used to verify both of them. To know more about torsion balance, see this part of the video. So this is what a torsion balance looks like. You have a torsion fiber over here. You have a charged sphere over here, another charged sphere over here, because of which there will be electrostatic force between these two spheres. And due to the force, there will be a torque, because we know that force multiplied by the perpendicular distance will give you the torque. This torque will try to rotate this, and there will be a restoring torque in the torsion fiber. When these two torques balance, it will stop, and according to that we will understand how much force was acting, because there will be an angle by which it will rotate, and according to that we will understand what was the force acting between them. So this is an animation. This sphere has been charged with positive charge, and this sphere has been charged with a negative charge. So there will be attraction between them, and how much it has rotated will be visible from this dial or even this dial. This is about it. Now, how does it work? This is a mistake. It's not a tension spring, it's a torsion spring. Now you know that in an extension spring, the elongation produced or extension produced is proportional to the load or force acting on it. है ना? So if you apply a force, there will be a restoring force, and that restoring force is proportional to the extension produced. More extension, more will be the force. And with that, we know the equation F is equal to Kx. You might have learned it in grade 11 already. But how does a torsion spring work? In this case, the angle by which this is rotating, or it's also called twist, the angle of twist is proportional to the torque on this spring. It is not proportional to the force alone, it is proportional to the torque. So we can see what is the torque acting here. If these two charges, now I have shown both negative, so there will be a force of repulsion. Now that force will be acting along this direction, and when this force is acting along this direction, we know the torque will be force multiplied by this distance. If the total length of the this rod is L, then the distance from the torsion spring or the torsion fiber will be L by 2. That's why I've shown torque is equal to force multiplied by L by 2. Now that torque is also proportional to angle, or the angle by which it is rotating is proportional to the torque. That's how torsion spring works. Okay, so because of that, and that's because T is equal to kt theta, as we know F is equal to kx for extension spring. Similar equation exists for torsion spring, which is T is equal to kt theta, where kt is the constant, spring constant. So because of this, we see that here torque is proportional to the force, because L by 2 is a constant. So, and also we know that the theta is proportional to T. So from these two relations, we get theta is proportional to F. So according to how much it has rotated, we know how much force is acting, or proportional to, what proportional force is acting. Okay, so this is what he did. He changed the charges on these, and continuously he did some experiments, and according to that, when the charge was halved, he found that the force is also halved. Charge on one I'm talking about. If charge on both were halved, he found that the force became 1/4. So clearly that indicated that force is proportional to product of Q1 and Q2. Similarly, when the distance between these were changed, he found that when the distance was halved, the force becomes 4 times. So clearly, the force is inversely proportional to the square of distance between the 2-point charges. So that's all. Now let's go back to the video. So that was about torsion balance. Now let's read on. When the separation between the two spheres is much larger than the radius of each sphere, the charged spheres may be regarded as point charges. However, oh, come on, this is the third time they are mentioning the same thing. So I'm not going to explain that. However, the charges on the spheres were unknown to begin with. How then could he discover a relation like equation 1.1? Now that's like a good question, because they did not know the charges on each sphere. Then how could they get to the equation, which is F is equal to k q1 q2 by r square? Let's read on. Coulomb thought of the following simple way. Suppose the charge on the metallic sphere is Q, which is unknown. We know that it is charged, but we don't know how much charge is there. If the sphere is put in contact with an identical uncharged sphere, the charge will spread over the two spheres. Now we know we take one sphere which is charged and we take another sphere which is uncharged. So what is the total charge in this system? Q plus 0. So Q is the total initial charge. Now if you bring them into contact, then what will happen? The charges will be equally distributed because they are identical spheres of same material. So charges will be equally distributed, and so it will have Q by 2 each. So now we have two spheres of equal charges, which is Q by 2 and Q by 2. Got it? Repeating this process, we can get charges Q by 2, Q by 4, Q by 8, etc. How? Suppose you have Q by 2. Now we know that one of the spheres is charged with a charge Q by 2. Take another identical uncharged sphere. If you touch them together, then what will happen? This Q by 2 will be equally distributed among these two spheres, and you will get Q by 4 and Q by 4. So like this, you can get different charges. Q by 2, Q by 4, and according to that you can do the experiment. Coulomb varied the distance for a fixed pair of charges and measured the force for different separations. So we have two variables here, charges and distance between the charges. So firstly, what he's doing is he's keeping the charges constant. Maybe he's taking Q by 2 and Q by 2, the spheres of charge Q by 2 and Q by 2, and then he tried varying the distance to understand how force is varying when the distance between them is varied. So suppose initially it is kept at maybe 10 centimeter distance, I'm just guessing, and then later on he kept at 5 centimeter or 20 centimeter and so on. So according to that he got how it is varying. Okay, so we have already learned about torsion balance. It will give an inclination or it will rotate. So how much it is rotating, that depends on the force, and so that depends on the distance. So maybe if the distance is half, he found that the force becomes 4 times. So clearly he understood that force is inversely proportional to not the distance but the square of the distance. Okay. He then varied the charges in pairs, keeping the distance fixed for each pair. Now he wanted to know how it depends on the charges. So he kept the distance constant. He's not varying the distance now. He's varying the charges. For example, he will take Q by 2 and Q by 2. Then he might take Q by 2 and Q by 4. And according to that, he found that the force is directly proportional to the product of the two charges. So that's how Coulomb arrived at the equation 1.1. Coulomb's law, a simple mathematical statement, was initially experimentally arrived at in this manner described above. While the original experiments established it at a macroscopic level or scale, it has also been established down to subatomic level. Now we were talking about spheres of charge. So it's a macroscopic level. We are not talking about atomic level or subatomic level. So this experiment was done in macroscopic level, and this law was derived or based on macroscopic level experiment, but it has also been established down to subatomic level. That means around radius of the order of 10 raised to minus 10 meters. Coulomb discovered his law without knowing the explicit magnitude of the charge. Yeah, we told that he did not know the charges, but he just found the relation between the product of the charges by taking Q by 2, Q by 4, etc. In fact, it is the other way around. Coulomb's law can now be employed to furnish a definition for a unit of charge. Yeah, he did not know the charges when he found this law. But actually, using this law, we can find or we can define the unit of charges. In the relation equation 1.1, K is so far arbitrary. We did not talk about the value of K. It's some arbitrary constant of proportionality. We can choose any positive value of K. The choice of K determines the size of the unit of charge. In SI units, the value of K is about 9 times 10 to the power of 9. So K is chosen such that the SI unit of charge becomes 1 coulomb. So if you are taking the SI unit of charge as 1 coulomb, it is found that the value of K is 9 times 10 to the power 9. What is the unit of K? We'll define later. The unit of charge that results from this choice is called a coulomb, which we have already defined earlier in section 1.4. Putting this value of K in equation 1.1, we see that for Q1 is equal to Q2 is equal to 1 coulomb and R is equal to 1 meter, the force is 9 times 10 to the power 9, right? Because from this equation here, if I put Q1 is equal to 1, Q2 is equal to 1 and R is equal to 1, so this entire terms becomes 1. So force is equal to K, whose value is 9 into 10 to the power 9, and the unit of force is Newton. So that's how you get it. So with this you can get that the force is very large. Come on, you're keeping 1 meter apart, the charges are kept 1 meter apart, still you get such a huge force. That means the unit of charge, which is 1 coulomb, is a very large unit. That's why in practical applications we use millicoulomb or microcoulomb, etc. That is, 1 coulomb is the charge that when placed at a distance of 1 meter from another charge of the same magnitude in vacuum, this is important, it is in vacuum, experiences an electrical force of repulsion of magnitude 9 times 10 to the power 9 Newton, which we have already discussed. 1 coulomb is evidently too big a unit to be used. In practice, in electrostatics, one uses smaller units like 1 millicoulomb or 1 microcoulomb. The constant K in equation 1.1 is usually put as K is equal to 1 by 4 pi epsilon naught for later convenience. For, when the units were chosen like that, it is convenient to write K as 1 by 4 pi epsilon naught. In higher classes you will learn that this is also coming from solid angle. The solid angle is 4 pi, just like the planar angle is 2 pi. Solid angle is 4 pi for entire rotation, for an entire sphere. It's not it's beyond the scope of the syllabus here. So that Coulomb's law is written as F is equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. So we previously, where K was there, we write 1 by 4 pi epsilon naught, and this is the Coulomb's law of finding electrostatic force, where epsilon naught is called the permittivity of free space, because we are talking about vacuum here. We talked about vacuum here. Okay, so that's why, I don't know where I saw it, we talked about vacuum. Yes, here. So that's why this is called epsilon naught as permittivity of free space or permittivity in vacuum, right? The value of epsilon naught in SI unit is 8.854 into 10 power minus 12 coulomb square per Newton per meter square. Now, how did we come across this unit? Let's check. If we rearrange, we can bring epsilon naught here and F can be brought here. So the equation will change to this way. Epsilon naught is equal to Q1 Q2, we are talking about the magnitude, divided by 4 pi F R square. So the unit of epsilon naught will be the unit of charge, which is coulomb, unit of charge, which is coulomb. So coulomb into coulomb is coulomb square, divided by unit of force, which is Newton, and divided by unit of distance square, because R is a distance. So clearly it will be coulomb square per Newton per meter square. Also we see that K is inversely proportional to epsilon. So that means unit of K will be 1 by unit of epsilon naught. Clearly it will be meter square Newton per coulomb square. So we did not talk about the unit of K here. The unit will be K is equal to 9 into 10 power 9 meter square Newton per coulomb square. Okay, that's all for today. That's all for today. And we'll continue from here in the next class. Until we meet again, I hope you like this video. Please give me a thumbs up and let me know that, and write something good in the comment section. So until we meet again, it's goodbye from me and happy physicsing.